Okay, good evening everyone. I welcome you all to the live session number 11 for NPTEL course Energy Conservation and Waste Heat Recovery. As of now, we have covered up to week 10 course content, and today we are going to see the course content of week 11. As you all aware that every Friday we are having a live session on which we discuss about some past assignment question, and we also discuss some concepts about the last week classes. So today we will cover week 11 course content, and let's wait for another 5 minutes. After that we will start. So let me see the lobby. Is anyone there? Okay. Okay, so we have waited for 5 minutes for students to join. Okay, now I think we should start. The question number one is melting refers to space and solidification refers to space in thermal energy storage using PCM. So PCM is phase change materials. So in thermal energy storage using phase change materials, what is the meaning of melting and solidification? That is the question. So take 2 minutes and let me know the answer. So PCM is phase change material. So in this type of energy storage system, what is the meaning of melting and what is the meaning of solidification? So let me give you a hint. So basically in phase change material, they can change phase actually. They can melt and they can solidify. In this way, they can store the energy. Maybe now you can relate like for melting or solidification. Okay, so let's go through the answer. So in thermal energy storage system using phase change material, the extra energy is stored by melting the phase change material. Okay, so like if we are having some extra energy, then we apply that energy and we will melt the PCM. Okay, so which is referred to as charging of the PCM. So the melting of the phase change material is referred to as the charging. So the first blank will be filled by the charging. So on the other hand, the stored energy is extracted from the molten phase change material by solidification, which refers to the discharging. So when we want to extract the energy back from the PCM, we will solidify it. Okay, and this is considered at discharging. So basically, melting the PCM for storing the energy is referred as charging, and solidification refer to the discharging, in which we are extracting the energy back. So the correct answer is option A. Melting refers to charging and solidification refers to discharging in thermal energy storage using phase change materials. Let's go to the question number 2. So what is and are the features of lead acid battery? So I think we have covered the lead acid battery. So what is and what are the features of these batteries? Option A is H2S or hydrogen sulfide is the electrolyte. During discharging, concentration of electrolyte decreases, bulky in size and self-discharge with time. Sulfation does not occur. So go through all the options and let me know the answer. Take 2-3 minutes. Okay, anybody? Okay, let's see the answer. So the correct options are B and option C. So the answer is the electrolyte solution used in lead acid battery is H2SO4. So H2SO4 is the electrolyte solution that is used in the lead acid battery, and during discharging phase, the concentration of H2SO4 decreases. Okay, due to formation of PbSO4. So during discharging, due to the chemical reactions, okay, the concentration of H2SO4 decreases and due to the formation of PbSO4. So the electrochemical reactions are there. So the lead acid batteries are bulky in size and the sulfation and discharging occurs with time. So now let's see the options. So the option A is H2 is electrolyte. So it is wrong. Why? Because we know the electrolyte is H2SO4. Option B is during discharging, concentration of electrolyte decreases. So it's correct because the concentration of H2SO4 is decreases due to the formation of PbSO4. So option B is correct. Bulky in size and self-discharge with time. So the lead acid batteries are bulky in size and the sulfation at discharging occurs with time. So both these things occurs with time. So option C is also correct. Sulfation does not occur. It is wrong because with time sulfation is also there. So correct answers are option B and C. So the lead acid batteries are bulky in size and self-discharge with time, and during discharging concentration of electrolyte decreases. Okay, let's go to the question number 3. What are the challenges in using hydrogen as fuel? Option A, high storage volume, toxicity, electrolysis of water, and flammability. Let's go through the option and let me know the answer. Basically, what are the challenges using hydrogen as a fuel? So let me give you some hint. Hydrogen is having highest calorific value and the density of hydrogen is very less. Think about it. Okay. So the correct answers are A and D, like high storage volume, because hydrogen, being the lightest gas, has a very high specific volume. Okay, because the density is very low, so it has a very high specific volume. As a result, storing even a small mass of the gas requires very large volumes. So for storing a very small mass of the gas requires a very large volume. Hydrogen is also highly flammable and the fire spreads rapidly due to its weight. It's lightweight. So hydrogen is very light, so its fire spread very quickly and almost I think in 1 kg there will be around 11 meter cube of hydrogen. Okay, it's approximately 11 meter cube of hydrogen in 1 kg, so you can compare it like the mass to volume ratio you can see. So we require high storage volume Okay, and the flammability is also very high. The option B is toxicity. So as hydrogen is not toxic because it is like it is it is only the hydrogen component in H2. So there is no toxic component in the formula. And electrolysis of water. So it is also not a challenge because easily we can do the electrolysis using electricity and some electrodes. Okay. So B and C are note the challenges for hydrogen as a fuel. Challenges are A and C. Require high storage volume and due to its high flammability. So correct answers are A and D. Let's go to the question number 4. End products of fuel cell is or are. So what are the end products of a fuel cell? Option A is oxygen, B hydrogen, C water, and D heat. So try to think about the class notes and let me know the answer. Do we have any answer? Okay. So in fuel cell, hydrogen atom and oxygen atom combines with each other to generate water. So as the process exothermic, as the process in exothermic in nature, and it generates heat. Okay. So basically, the hydrogen is fuel in fuel cell, and oxygen is also supplied. Okay. So basically, we supply hydrogen and oxygen, and there are some electrochemical reactions are there. They generate heat and water. So the end product is water and heat. Oxygen and hydrogen are supplied product. Okay. So we supply oxygen and hydrogen to fuel cell. So these are, you can say, the input or raw material, and water and heat are the product. Okay. So the end products of a fuel cell are water and heat. So the correct options are option C and D. In a PEM fuel cell, calculate the cell potential for a work done of 200 kilojoule. Faraday's number F is 96485 and the number of electrons per mole of fuel N is 2. So calculate the cell potential for a work done. You have given a work done, okay, and you have given the Faraday's number F. The number of electrons per mole of fuel is N is 2. So let me know the voltage. So let me give you a hint. The work done for a fuel cell is NEF. Maybe now you can try to find the answer. Because we have given F, we have given N, we have also given W. Try to solve the equation. Okay. So write down the given data. Okay, we have given W, so it's 200 kilojoule. So 200 into 10 to power 3 joule equals to, we have given the electrons, N equals to 2. E we have to find out. F we have given 96485. So the E will be 200 into 10 to power 3 upon 2 into 96485. It will become into 1.03 volt. So 200 multiply 10 to power 3, because we have given the kilojoule, and 2 multiply 96485. Okay, we have to divide these, and the voltage will be 1.03 volt. Okay, so the correct option, the nearest option is option A, 1 volt. Okay, so this is the formula. The work done is NEF. Okay. So what is a typical value of thickness of the catalyst layer in a PEM fuel cell? So try to remember this. Okay, what is the typical value of thickness of the catalyst layer? So you know there is a catalyst layer in PEM fuel cell. To perform the electrochemical reaction in the fuel cell. So what is the typical value of thickness of that layer? 100 micrometer, 10 micrometer, 20 micrometer, and 1 mm. Okay, let me know the answer. So what is the thickness of the catalyst layer? let me give you some hint. The PEM fuel cell is polymer electrolyte membrane fuel cell. Okay. So in this we use Nafion as a membrane. We supply hydrogen, we supply oxygen, and it is a low temperature fuel cell. And it is the best option, like it is the best fuel cell that can be used in automobiles due to its low temperature of operation. So the correct answer is option B. So the thickness of catalyst layer is in PEM fuel cell is 10 micrometer. Okay. For more detail, you can refer the lecture 61. Let's go to the another question. So what is the function of gas diffusion layer in PEM fuel cell? Now, what is the function of this gas diffusion, this GDL, a gas diffusion layer? Option A, prevent heat loss during storage, distribute reactants uniformly, connect the catalyst layer to the bipolar plate electrically, and provide structural strength. So let me know the answer. Think about it. So try to think about the function of gas diffusion layer, or in short, GDL, in PEM fuel cell. So GDL is basically a very small layer, very thin layer on PEM fuel cell. And you can also look carefully the name, the gas diffusion layer. Maybe if you think carefully, then you will understand the meaning of gas diffusion. What can be the purpose of this layer then? As name suggests, gas diffusion layer. So basically, this layer is used to diffuse the gas. Okay. So the correct answer are B and C. So basically, gas diffusion layer distribute reactants uniformly. So basically, we want to distribute the reactants uniformly so that they can have proper electrochemical reactions. Okay. So that's why we apply this layer. And it also connect the catalyst layer to the bipolar plate electrically. So it also connect the catalyst layer to the bipolar plate electrically. So to make a to make a connection between the catalyst plate and to the bipolar plate. So option B and C are correct. Prevent heat loss during storage. So no, because we are not storing or we are not doing something. We want this layer for the proper electrochemical reaction in the fuel cell. So option A is wrong. Provide structural strength. No, it's not for structural strength. It is basically to distribute reactant and to connect the catalyst layer to the bipolar plate. Option D is also wrong. So correct answers are B and C. Option number 8. N-hexadecan, an organic phase-change material or PCM with melting point of 18 degrees centigrade and specific gravity of 0.6 is used for building air conditioning. The PCM chamber has a volume of 3 meter cube. If the latent heat of fusion of an hexadecan is 225 kJ per kg, calculate the energy storage capacity of the unit. So you have given some data. Okay. So now you have to find out the energy storage capacity of the unit. So you have given the melting point of the PCM, that is 18 degrees centigrade, specific gravity, that is 0.6, and the PCM chamber volume 3 meter cube, and the latent heat of fusion of N hexadecan is 225 kilojoule per kg. Now calculate the energy storage capacity of the unit. It's a numerical, quite important for your exam. Take 2-3 minutes and let me know the answer. Anybody? You have to find the energy storage capacity. You have given the latent heat of fusion. Maybe you can think about that. You have given a volume, specific gravity. So maybe from that you can find the mass, and you have also given the enthalpy. Then if you multiply those, then that can be the storage capacity. Think in this direction. Let me know the answer. Any answer? Okay. So let me give you the formula. The formula maybe you can use is E equals to, so the stored energy will be mass, enthalpy of storage PCM, okay? The compound which you are using for storage, enthalpy of that. So M into H, enthalpy. So you have to find out the H, I think you have given already. To find out the mass. So you have given volume and specific gravity. I think from that you can find out the mass. So maybe we can write mass as a rho V H ST. So I think now we have H, we have V volume, now density, but we have given the specific gravity. So now let me know the answer. Okay. So we have specific gravity as 0.6. So for density, we can multiply it by 1000. Okay. So the stored energy capacity will be, so the density will be 0.6 into 1000. Okay. Volume V 3 meter cube, and enthalpy is 225. It will be 600 into 3 to 225, or it will come out 40500 kilojoule, or you can write 405 mega. So now see the options. So A, B, C, it's option D. 405 megajoule is the correct answer. Option D. Okay. So whenever you have given data like this for PCM and you have to calculate the energy storage capacity, then you can multiply the enthalpy with the mass. Okay, for mass you can write it like density into volume, and for volume you have given volume. For density you can use a specific gravity. In this way you can find the answer, and that will be 405 megajoule for this particular question. So in the previous question, you can use like the PCM to be frozen, like in this question, okay? If outside air at 35 degrees centigrade, so you have given further the outside air is at 35 degrees centigrade to be cooled down to 20 degrees centigrade by the phase change material and supplied indoor from 9 a.m. to 4 p.m. What should be the maximum mass flow rate of air? Okay, you have to find out the maximum mass flow rate of air. Neglect sensible heating of PCM and assume specific heat of air to be 1.0 kilojoule per kg Kelvin. So you have given some conditions regarding outside air at 35 degrees centigrade that has to be cooled down to 20 degrees centigrade by the phase change material and supplied indoor from 9 a.m. to 4 p.m. So what should be the maximum mass flow rate of air? Okay. So you have also given the specific heat of air as 1.0 kilojoule per kg Kelvin. So let me know the answer. Okay. So let me give you some hint. So the energy stored can be also written as okay, because you have given the conditions, okay, you have given the exchange material, so the energy stored will be equal to this. And in previous question, you have already calculated the stored energy for this hexadecan exchange material, that is 405 megajoule. So you calculate the energy stored, that is 405 megajoule, or you can say 10 to the power 3 kilojoules. Okay. So now I think you can find the answer. You have given Cp, you have T naught and Ti. So let me know the answer. T naught is outdoor temperature, Ti is the indoor temperature, Cp is the specific heat, M will be the mass flow rate. So you have to calculate the mass flow rate. I think from this energy equation, you can calculate the mass flow rate. You have to just put the data. Take another 2 minutes to and try to find the answer. Let me know. You have to put the data and you can find the answer. So the mass flow rate, I think we have to find. So it will remain same. Then Cp we have given 1.0 kilojoule per kg Kelvin. Actually, we have Cp in kilojoule. That's why we have wrote this energy in kilojoule because it was in megajoule, 405 megajoule. So now we are writing it in kilojoule. Okay, because Cp is also in kilojoule. Now the outdoor temperature is 35 minus indoor temperature is 20. So now if we further solve it, will look like this. Okay, mass flow rate will be 405 multiply 10 to the power 3 upon 1 multiply 35 minus 20. Okay, and we have to also multiply the time. Okay, we have given it will be into time also. because we have given the time also, 9 a.m. to 4 p.m. So it will be, and it will be it will be 7 hours, and we will count in the seconds. So multiply it 7 into 3600. So after solving, you will get 1.071 kg per second. And the nearest option is option A. Okay. So more clearly you can see like this. Okay. So using the equation mCp T naught minus Ti into time equals to energy stored. So now m will be put all the data 405 multiply 10 to the power 3 upon 1 multiply 35 outdoor temperature minus 20 indoor temperature multiply 7 into 3600 time in seconds. So it will be in kg per second. So the answer is 1.071. The correct option is option A. 1 kg per second, the nearest answer. Question number 10. In a sensible thermal energy storage system, storage tanks 5 meter in diameter is used to store water from 2 bar to 20 bar. So we are having a storage tank that has a diameter of 5 meter, and it is used to store water from 2 bar to 20 bar. Assuming water mean density and specific heat to be 960 kg per meter cube is the water mean density, and specific heat is 4.35 kilojoule per kg Kelvin. Okay, and overall heat transfer coefficient between the stored liquid and outside ambient to be 1.5 watt per meter square Kelvin. Now calculate the time constant for the system. You have to calculate the time constant for the system. You have given the diameter, you have given the pressure from 2 bar to 20 bar, and water mean density you have given, specific heat you have given. Okay, you have to calculate and you have given the overall heat transfer coefficient. Now calculate the time constant for the system. Time constant you have to calculate. Okay, any answer? So let me give you a hint. The time constant is tau equals to B rho Cp upon 4U, where D is the diameter, rho is density, Cp is the specific heat, and U is the universal heat transfer or the overall heat transfer coefficient. Okay. Now try to put all the data and let me know the answer. We have given all the data. Maybe you can try the calculation. It's quite an important question for exam. Okay, so when you put all the data, okay, you will get tau is 966 hours as the answer. You have given the D, dia 5 meter, density 960 kg per meter cube. Okay, you have given rho Cp 4.35 kilojoule per kg Kelvin and 4 and U 7.5 watt per meter square Kelvin. So you're given all the data, you just put it, and the answer will be 966 hours. Okay, option D. So these are the questions for today. Now let's see some theoretical concept. And I think we have one student in our class. Okay, Prashant. Prashant, hello. Am I audible, Prashant? Okay, Prashant, please let me know that my audio is clear and my PPT is also visible. Because I think you are the first student today online.
Just coming from my office and login.
Okay, okay. So it's everything is okay? Video and audio?
Sir.
Yeah, okay, okay, thank you. So the latent thermal energy storage or phase change material. So in phase change material, we have certain materials that can change phase, okay? That can be liquefy or solidify. Okay, so they absorb heat and they will become, they melt and store the energy, and if you take the energy, they again solidify. So you can see absorb, then they store, and then they release. So if they store the energy, this will be in liquefied, and when they release the energy, it will again become solidified. So you can see the enthalpy versus temperature curve. So if you are increasing the temperature, if you are giving the, if you are heating it, then you can see the temperature is increasing, but at a certain point only the temperatures remain constant, but enthalpy is increasing. Okay,
Yes, sir.
because, sorry,
Yes, sir.
yeah, are you saying something?
No, sir, no. Just some confusion, sir. That is a two graph. One is for red color showing in red, and other is a blue color
Yeah,
for ideal.
yeah, yeah.
So it is only for what is the difference into red is for absorption and green is for
Okay, these one and two, no? Yeah,
yes, sir.
yeah, yeah. Ideally, it should be like this. Like there should be a, like sharp changes should be there in ideal condition, like when they are changing the phase. Okay, but in actual, it is not like sharp. It's like this. And actually, I'm also not aware of the main reason behind this. So maybe you can refer to the class notes for more detail.
Okay. But sir, in ideal, there is a tool that is graph. One is showing in red color and other is in I think blue color.
Yeah, blue color. Yeah.
So both is for same uh, or purpose, any other purpose behind it, sir?
Yeah, actually, a good question. I have to also check this. Okay, I think you are talking about this one and this one.
Yes, sir. Yes,
Yeah,
sir.
yeah. I think I have to check this also. I'm not fully aware about it. But the main point, this point is this section is showing the phase change actually,
Yes, sir.
and this section is showing like initial heating from a
Rating
particular
and
temperature to a particular temperature that there will be the phase change will occur. Then there will be phase change. It will melt, and again it will increase in temperature, so it will store more energy in it.
sir.
But I think there are two, so there is a reason for two. But okay, I think yeah, I think one is
Material,
okay. Yeah,
material for
yeah.
material.
Yeah. One is for the, yeah, I get the point. Okay. So this red one, it will be the during the first, during the you can say the when you are supplying, when it is storing the energy, and this one will be when it is losing the energy, I think. That's why it's red, and that's why it is in blue. Okay. So
But sir, say if it is applicable only for same material during a heat process, supplying process, when it comes, we started from absorbing heat, then phase change, then going heating, it follow the red and same material from that temperature. If you go on reverse side,
reverse,
then
then it will follow the blue.
follow blue, but the path will be different. Means it will not follow same path when it is uh, heating process. If material is
Yeah,
cooling
yeah,
from the temperature, so
yeah,
it
yeah. I
should not
think
go
I
that.
think it is the reason. Actually, I have to check. I just actually I'm not fully aware of this, but as I know, I think it should be the reason. So it is for
Okay,
the
sir.
ideal
No,
condition. Actually, we have to check the
hmm,
class notes. I am
sir.
also not fully sure about it, but I think so. I think so. I think because these are the color coding one, red is for, I think, uh, the heating, and the blue one is for, I think, cooling. I'm not fully sure. We have to check it.
Sir.
Okay. So the next is solar power with thermal energy storage. So in this, we can we can use the solar power, and we can store thermal energy. So here we can see some solar plates. Okay. You can see there is some arrangement from where we can tap the solar energy. There are some pipes, and there's the whole piping connections are there. The one is thermal energy storage, a heat exchanger is there, then hot salt, then the steam boiler, then steam turbine, then here we are generating the generator, generating electrical energy, then again heat exchanger. So basically, you can see when there is a, you can see that there is a fluid passing through these pipes. Okay. So the solar energy is giving heat to these pipes, and you can see the fluid is flowing through this circuit. So in the daytime, we know that we can use the solar energy, okay, and we can store that heat, and during night we can use it. So like if you are having like liquid is going through this, and here it's going to this heat exchanger. So in heat exchanger, it's flowing through like this, okay. So here we are having water. So water is going from here to here. Okay, so this water is cold water, and this is steam, and this is hot, this is cold. So this fluid is having high energy. So in this heat exchanger, it is giving its energy to water, and water is converting to steam. And during this fluid is losing its energy and it's becoming cold. Okay. So the steam is generated. Now steam is going to the steam turbine, and it's generating the electrical energy that is supplied to the housing or to the cities or towns. Now the remaining water is again coming here. Again, it is losing heat in condenser. Okay, and again we are having the cold water, and this is the same cycle is going on. So there is again a thermal energy storage. So if we are having excess water, then then here we can apply a junction. Okay, so some extra water, like some extra fluid that is here, that is taking the solar energy, so that will go into this section. Okay, and here we have like solid salt and molten salt. So this is flowing like this. So uh, this fluid will supply its energy to this salt, and it will become hot salt, or it will become melt and store energy. So we can store energy here. Okay, it will lose energy, and again the cold fluid will go through this. Now, if we are not having the suppose if we are not having enough solar energy, then what we can do? This will reverse. So this hot salt now supply the energy to this fluid, and it will become heated, and this salt will become again come to this action. Okay, in this way we can store the energy, and we can. So this is use of solar power with thermal energy storage system. Another one is air conditioning and ice formation. So standard chillers runs at night to produce an ice pile. And water that circulates through the pile during the day to produce additional chilled water to meet peak demand. So you can see we are having some chillers. Okay, so we are supplying the chilled water, uh, like in office spaces, or like you can say in colleges, in like large buildings. So there we are not using like normal air conditioner. Okay, so we are using these chiller units. So basically we are supplying chilled water through those radiators or those pipes, and the air is circulating around those pipes. So in that way we are meeting the cooling demand. Okay, so if we are having additional, like if we are like suppose there is like there are no like if
Sir, excuse me, sir. Can I
yeah
hold, sir, video for, because sir, I'm only one participant in the video, so I request whether I will keep it in hold, or it will because I have some urgent work from official purpose, so
yeah, sure, no issue,
so
sure,
please sir, don't mind, please. Huh?
yeah.
Otherwise, sir, you can continue, sir, because I take some time for that work. Uh,
Yeah,
so,
okay, yeah.
thanks.
So here you can see that, so the hot water is going on, and if we are having like less demand, suppose during like on some weekends there are no students, or like there are less number of people in the building, so in that case we require less cooling. So in that time we supply the chilled water to generate or to form the ice, and if we are having more demand, then we can use that ice to again generate the cold water to meet the cooling demand. In this way we can store the energy, and we can meet our peak rate demands. So this is a patient material for building energy storage. Okay, this is a diagram showing from time of the day, and there is a load on arbitrary scale in megawatts. So you can say like during the daytime from 12 hours to 19 hours. So this is a peak time. So the demand is very high. Okay. So this is the peak load power plants. Okay. This is the intermediate load power plants, and this is the base load power plants. And this is the typical demand curve, and this is a demand curve. This like this dotted line is a demand curve with the thermal energy storage. So you can see with the TES we have eliminated this section. That was the peak load power plants demand. We have eliminated this section by using TES. So this is a passive storage building envelope. So here also we are using a phase change material so that uh, these doors are like storing the energy, okay, and they have reduced the energy required for heating or cooling. So we are adding the phase change material to insulation, okay. So 33% less peak heat flux and 13% net heat gain. Okay, so 33% less peak heat flux and 13% decrease in net heat gain. Okay. So this is again a diagram for passive versus non-passive thermal energy storage. Now the electrochemical energy storage, it's quite interesting. So electrochemical energy storage. So here the first is battery. Just give me a moment. So batteries are the stack of individual cells, and cells comprises of anode and cathode in an electrolyte. Okay. And the electrical energy is delivered during discharging cycle. And various cells chemistry are used like lead acid battery, nickel cadmium battery, silver zinc battery, nickel metal hydride battery, and sodium halide. So these are different types of cell chemistries that are used. You can see the materials like lead peroxide is positive electrode, spongy lead is negative electrode, and diluted H2SO4 is electrolyte. Okay, and the overall reaction is Pb plus PbO2 plus 2H2SO4, and during the discharge it will convert into 2PbSO4 plus 2H2O, and during the charge it will again become Pb plus PbO2 and 2H2SO4. So during discharge the concentration of electrolyte is reduced due to removal of sulfate ions and formation of water. So you can see the water is forming and the removal of sulfate ions during discharge. And the features are like used in cars, series of 6 cells, flexibility in current or high reverse flexibility in current and high reversibility, and self-discharge and sulfation occur with time. Self-discharge, I think we have also covered a question on it. So self-discharge and sulfation occurs with time. Other forms of battery like nickel cadmium battery. So cathode is nickel hydroxide, anode is cadmium, and electrolyte is 50% KOH. Silver zinc battery, anode is zinc, cathode is Ag, and electrolyte is KO solution with zinc hydroxide. These batteries have high energy to mass ratio and greater life cycle compared to lead acid batteries. And now the chemical energy storage. So heat of reaction of reversible chemical reaction is used to store the thermal energy. during endothermic reaction and release it during the exothermic reaction. So you know that some reactions are there, so they are having exothermic or endothermic. Okay, so there is a particular temperature on which after that they really the reaction happens, and if we go below that temperature, then the reverse of that reaction will happen. So it can go in both direction. Okay, so you can see the methanation and reformation reaction. So the methanation is exothermic. So when the CO plus 3H2, if these two meet, then they form the CH4 and H2. So this is the methanation and it's exothermic. It will release heat. But if you reverse it, so it require heat. It's endothermic. It's reforming reaction. It's very popular reaction is steam methane reforming. Basically, we are supplying steam and we are reforming the methane to hydrogen and carbon monoxide. Okay, so this is a very famous steam reforming reaction or reformation reaction. It is endothermic. It require very high temperature, and the other one, if reverse of is this methanation reaction, that is exothermic reaction that will release the heat. So there is a reactor, suppose. So if you are supplying CH4 and H2O, so you need 250.3 kilojoule per gram mole of energy to form CO and 3H2. If you reverse it, then if you have these two, then you will release this much of energy to generate these two. So this is a chemical energy storage. Now thermochemical storage. So direction of reaction reverse at turning temperature T star. Okay. So T star is the turning temperature. Reversible reaction AB to A plus B or A plus B to again AB. So temperature above T star, reaction shifts to right. So if the temperature is above T star, then reaction will go to the right side. So AB will become A plus B. If temperature below T star, then reaction shift to left. So A plus B will become AB. So it depends on the T star temperature. Only reaction producing two distinct phases, example solid or gases, considered suitable since reactants are easy to separate and store. So if we are having two distinct phases like solid and gas, then they are considered suitable since reactants are easy to separate and store. Like NH4F, it's solid, NH3 again gas, and HF gas. So the T star temperature is 499 Kelvin. So if the temperature is above T star, then reaction will go in forward direction. If temperature is below T star, then reaction will go in backward direction. So NH3 plus HF will become NH4HF. Similar like MgOH2 is solid and become MgO solid plus H2O. So it will be uh, liquid. Okay. So in this we are having two phases, and this CaOH2S or CaOS plus H2O gas, or you can say steam. So in this we can also easily separate these. Now the hydrogen economy and fuel cell. So hydrogen as fuel, so it is highest energy content per unit mass, that is 141.9 megajoule per kg. It's very high, 3 times of gasoline. Okay, so the energy content of hydrogen is 3 times of gasoline. Energy per unit volume is very low due to low density. So the density of hydrogen is very low. That's why energy per unit volume is very low. Hydrogen is not a readily available fuel, and it makes up to 75% of matter in universe, but it is scarce in free form. So like hydrogen is the main, like is behind 75% of matter in universe. Okay, but it is not available in free form. It is combined with some components like H2O, combined with oxygen, CH4, combined with carbon like hydrocarbons. Okay, so it is already like mostly like it's not available in free form. So history of hydrogen economy. So the first vision was by Jules Verne. In his science fiction adventure, Mysterious Iceland proclaims water will be the coal of the future. And discovery William Groove demonstrated fuel cell operating principle in 1839, and around the same time, Christian Sonneben demonstrated it independently. Okay, and the production and storage. So Haldane predicted that hydrogen derived from wind power by electrolysis liquefied and stored will be the fuel of future. Application and transport. So I think it's Levjek outlined the concept of hydrogen powered vehicles in 1920s, probably the first to suggest that hydrogen could be transported via pipelines similar to the natural gas. Then Bockris in 1962 sets down concept of solar originated hydrogen economy named by Bockris and Trinell 1970, later formulated and quantified by Bockris and Appleby 1972 and Georgi 1972. Now the hydrogen production requires feedstock and energy. So we require a feedstock and supply the energy. Present methods of hydrogen production, currently we mostly the 75% of production like is using steam reforming, or we are having biogas gasification, steam reformation of bio oil, partial oxidation of hydrocarbons, coal gasification. The cost is around $6 to $15 per gigajoule. Its cost is very high, and electrolysis of water is costing around $20 per gigajoule. So it is very high cost. Okay. So these are the method, and most popular is steam reforming method. Now we are shifting towards the electrolysis of water. So the scientists are working to decrease the cost of electrolysis, so that can be called green hydrogen, because we are using the renewable electricity to generate the hydrogen. So there are some challenges of hydrogen as fuel, like storage, like large volume for a given mass, okay, and compressed gas storage. Compressed gas storage in underground tanks, compressed storage and transportation in pipeline, liquid hydrogen, like energy intensive process and transport is hazardous. Metal hydrides, like higher density but safe, absorb gas at room temperature, release on slow heating. Platinum PD are very expensive. Glass microspheres, doped glass microspheres used to store and release hydrogen. So these are like methods we can store in metal hydrides. We can use glass microspheres. We can use a liquid hydrogen. We can compress and store it. Okay. So these are the things in storage. Combustion. Hydrogen is highly combustible, and flame is invisible and spreads very rapidly. So these are two challenges in combustion. Now safety of hydrogen fuel. So hydrogen could be unsafe if handled improperly, because it is highly inflammable and invisible flames. So hydrogen could be unsafe if it handled improperly. So because it is highly inflammable and invisible flames. Historically, two incidents have severely tainted its reputation as a safe fuel. First was the Hindenburg incident 1937. So no conclusive proof that accident was triggered by combustion of hydrogen. And the second one is the hydrogen bomb has no relation with energy storage application other than sharing part of the name. Now come to the fuel cell. So fuel cells are like quite important and a good technology, clean technology. Okay, they are quite popular nowadays. So let's see. So fuel cell converts the chemical energy from a fuel directly into electricity. So converts the chemical energy from fuel to directly into electricity. High efficiency, low noise, stable power generation, reduce expensive power transmission, and less polluting. So you can say this is a fuel cell stack of proton exchange membrane. There is a membrane, okay. There is electrical connection. There is anode, cathode. Red one is the hydrogen, blue one is oxygen, green is power on or positive, and this one is electron. So we are supplying the hydrogen fuel on the anode side. You can see, okay, and the oxygen from the cathode side. Okay, and here you can see there is a gas diffusion layer, and there is a catalyst, which are also a gas diffusion layer. So this membrane will pass the hydrogen ion, and the electron will go through the outer circuit, and we get the electrical output. And here the hydrogen ions will combine with the oxygen ions and will form the water vapor, and the reaction will release heat also. So fuel cell and battery. So fuel cell, like chemical fuel continuous flow, but in battery chemical stored inside. So in fuel cell we have continuous flow, but in battery we have limited fuel only, that is already stored in the battery. This is the difference between fuel cell and battery. So fuel cell produce electricity continuously for as long as fuels are supplied. So we can get electricity as long as we have enough fuel. Battery eventually goes dead after a certain period because the fuel is already inside, like in some battery containers, or like in the battery itself. So it will eventually goes dead after a certain period. So we have different kinds of fuel cell: proton exchange membrane fuel cell, direct methanol fuel cell, alkaline fuel cell, phosphoric acid fuel cell, molten carbonate fuel cell, and solid oxide fuel cell. So every fuel cell is have their own different type of characteristics. Okay, like the operating temperature and what kind of electrolyte they use, what kind of mechanism they use. Okay, so let's see. So the first one is proton exchange membrane fuel cell. So here you can see the operating temperature is 80 degrees centigrade around, and the fuel is hydrogen on the anode side, and the H2O is the output, and O2 is the on fuel is the on cathode side, and the electrolyte passes the H plus ion. Okay. In direct methanol fuel cell, you can use CH3OH as a fuel. The H plus ion transported through the electrolyte, oxygen is supplied through the cathode, and water is generated at cathode side, and CO2 is at anode side. Then alkaline fuel cell, then hydrogen is the fuel. OH minus ion is the transported through the electrolyte towards the cathode, and oxygen is supplied at cathode side. Water is generated at anode side. Phosphoric acid fuel cell, like for direct methanol fuel cell, operating temperature 80 degrees centigrade. For alkaline fuel cell AFC, the operating temperature is around 100 degrees centigrade. The phosphoric acid fuel cell, hydrogen is supplied towards anode, oxygen is supplied towards cathode, H plus ion transport from anode to cathode, H2 is generated at cathode. Operating temperature is 200 degree centigrade. Molten carbonate fuel cell, hydrogen is supplied at anode, oxygen supplied at cathode, then carbonate ion is supplied from cathode to travels from cathode to anode, H2 and CO2 generated at anode. SOFC, hydrogen is supplied at anode side, oxygen is supplied at cathode side. Oxygen ion travel from cathode to anode, and water is generated at anode. So this is anode, electrolyte, cathode, and temperature is 1000 degree centigrade. For MCFC, temperature is about 650 degree centigrade. So these are the some characteristics of proton exchange membrane fuel cell, like PEM fuel cell, DMFC, direct methanol fuel cell, AFC, alkaline fuel cell, PAFC, phosphoric acid fuel cell, then molten carbonate fuel cell, and solid oxide fuel cell. So this is a detailed comparison. So basically we have two types of segment. One is low temperature fuel cell, and the another one is high temperature fuel cell. So low temperature fuel cell, DMFC or PMFC. So they are direct methanol fuel cell or proton exchange membrane fuel cell. Electrolyte is proton conducting membrane. In both PMFC, proton conducting membrane. Temperature range is less than 100 degree, less than 100 degree. Fuel will be methanol in DMFC, hydrogen in PMFC. Power ranges like watts to kilowatt, PMFC watts to kilowatt. Application areas, vehicle, small application for DMFC, PMFC, vehicle, small generators, domestic supply, low type heat and power station. The other one is AFC, alkaline fuel cell, then caustic potash solution is the electrolyte. Temperature range is less than 100 degrees centigrade. Fuel is hydrogen. Power range watts to kilowatt. Application area space. Then medium temperature fuel cell, or you can say PFC, phosphoric acid fuel cell. Concentrated phosphoric acid is electrolyte. Temperature range is 200 degrees centigrade. Fuel is hydrogen. Power range is kilowatt. And application area is low type heat and power stations. Then high temperature fuel cell is molten carbonate fuel cell. Molten carbonate is the electrolyte. 650 degrees is the temperature range. Fuel is natural gas and coal. Power range kilowatt or megawatts. Application area is power plants, combined heat and power. SOFC is solid oxide fuel cell. Ceramic electrolyte. 8000 to 1000 degrees centigrade is temperature range. Natural gas or coal is the fuel. Kilowatts or megawatts of power range. And application areas like power plants, combined heat and power plants. Now the brief history about polymer electrolyte membrane fuel cell. So Sir William Groove demonstrated fuel cell operating principle in 1939. Around the same time, Christian Suneben demonstrated it independently. Then Francis T. Bacon started working on practical fuels in 1937. And by the end of 1950s, he was able to develop a 6 kilowatt fuel cell. General Electric developed first polymer electrolyte fuel cell for the Gemini program in 1960 for NASA. This was followed by Apollo program where Pratt and Whitney built fuel cell based on Bacon's patent. General Motors experiment with fuel cell powered van with cells from unicorn carbide in mid 1960s. Although fuel cell was a great success in space program, it was all but forgotten in terrestrial application. In 1989, Perry Energy System and Ballard demonstrated a PFC powered submarine. In 1993, Ballard demonstrated PFC powered buses. Energy Patents, a successor of Perry Energy Systems, demonstrated the first PFC powered passenger car. So this is the re-entry of the fuel cell in the market. So so proton membrane fuel cell is typically operated at 2 atmosphere and 80 degrees centigrade with partially humidified, you can say 50 to 70% fuel and oxidant. Typically current density is 0.2 to 1 ampere per centimeter square and voltage is 1 volt to 0.6 volt. Typical dimensions like membrane 30 micrometer, catalyst layer 10 micrometer, gas diffusion layer is 200 micrometer, gas channel 1 mm dia and cell platform area 100 centimeter square. Typical materials like Nafion membrane, carbon supported platinum catalyst, carbon paper cloth diffusion media and graphite bipolar plate. So these are some conditions for PMFC. So chemistry and thermodynamics of PEFC. Anode reaction is H2 becomes 2H plus 2 electron. Cathode half H2 plus 2H plus 2 electron become H2O. Overall H2 plus half O2 become H2O. The heat of reaction is delta HHB 286 joule per mole. LHB 241 joule per mole. Delta G is equal to delta H minus 3 delta S 237 joule per mole. This gives free energy. Okay. The electrical work is NFE, where WEL is electrical work, N is number of electron per mole of fuel. You can see here 2 electrons are participate in this reaction. F is Faraday's number of charge per mole of electron. E is potential. From this you can find out the work or potential. Now cell potential and energy efficiency. Now assume that all the Gibbs free energy could be converted to electrical energy. electrical work. So the maximum cell potential will be E equals to minus delta G upon NF. So put the value of delta G, that will be 237,340 upon 2 multiply 96485, it become 1.23 volt. So this is the maximum volt that a fuel cell can generate. The maximum energy efficiency of the system will be delta G upon HHV. So it will become 83%. If you use LHV, it will become 94.5%. The main point is that the Carnot efficiency myth, that fuel cells are not governed by the Carnot efficiency because they are not a heat engine but an electrochemical engine. Okay. Therefore, Carnot efficiency limit is not applicable here. So the efficiency can be more the Carnot efficiency, that will become 83% or 94.5%. But in actual, we are having efficiencies around 60% or 65%. So PFC components like solid electrolyte polymer membrane. So PFC derives its name from polymer electrolyte membrane. These membranes are solid electrolytes that conduct proton but are impermeable to gaseous phase. So these membrane can conduct proton but are impermeable to gaseous phase. Okay. Material, typically these are perfluorocarbon sulfonic acid ionomer PSA. Okay. This is essentially a polytetrafluoroethene PTFE attached with perfluorosulfonic and acid monomers. The best known membrane is Nafion by DuPont. Thickness is 20 micrometer and their properties are high proton conductivity, chemically inert, mechanically strong against swelling. In PFC, the electrode is thin catalyst layer placed between electrolyte and gas diffusion layer, and all the desired reaction take place at the site and current is produced here. Platinum is the best material so far, but a big hurdle to commercialize due to cost. Efforts on the develop low-cost alloys that could replace the platinum, and thickness is less than 10 micrometer, could be thinner in anode side, and desired properties are high reactivity, resistance to corrosion, and coagulation. The gas diffusion layer, I think we have also a question about it. So this is layer between the catalyst layer and bipolar plate roll. I suggest that its porous layer is for distributing reactants evenly to reaction sites and remove product. So this is used for distributing reactants evenly so that the electrochemical reaction can happen smoothly and evenly and remove the product. It has another equally important task of electrically connecting the catalyst layer with bipolar plate. So it is also connecting the catalyst layer with the bipolar plates. High thermal conductivity to remove the waste heat. Material, carbon paper of carbon cloth. Thickness, it is having thickness like 100 to 200 micrometer. May also include microporous layer. So high porosity to ensure gas phase diffusion and hydrophobic to help remove liquid water. High electrical conductivity and corrosion resistant. So these are the properties for gas diffusion layer, or you can say GDL. Bipolar plate. So this is the outermost component. Gas channel supply reactants and remove products. Okay, roll. It connects the outer circuit and drive current. It removes the waste heat. It provides structure strength to the cell. So the structure strength is provided by the bipolar plate. Material like graphite has been the common bipolar plate material, and various research are going to on use coated stainless steel as a bipolar plate. Thickness is 1 mm. It is high electrically and thermal conductivity and corrosion resistant mechanical strength. Water balance. So water is essential to proton exchange membrane fuel cell operation. To maintain high proton conductivity, membrane must remain well hydrated. Water is produced in cathode catalyst layer, which is adjacent to the membrane. Too much water results in condensation and therefore blockage of electrode and gas diffusion layer pores. So at low stoichiometry operation, liquid water might block the gas channel. So we need like a optimum water quantity at the membrane so it will remain hydrated and work efficiently. Proton drags water from anode side to cathode side due to electroosmotic drag. resulting in anode dry out and cathode flooding. This is also a case. Therefore, it is absolutely necessary to maintain a proper water balance in PEFC. So, proper water balance is important in PEFC. So, I think this is today. This is for today's class. So, we have covered some basic concepts about fuel cell energy storage, and we have covered previous year assignment question. So, I think, but we still have some time available. So, floor is open. Anyone can ask question. If anyone is having any doubt regarding the questions and concepts, let me know. I'm visiting the all slides. If you have any question in between, please let me know. If you have any doubt, please let me know. you have any doubts, please let me know. Please let me know if you have any doubt. So I think we have covered past assignment question, and we also covered some concepts. So I think you all learned a lot from this, and I hope you will also join our next class on next Friday from 7 to 9. So thank you all for joining, and I'm ending today's meeting. Thank you, thank you, thank you, everyone.